before its final talk, Bill Browder of Princeton is going to say a few words.
Official title, Bill Browder. It's my great pleasure to welcome the Gitler family and all of them here. And what good luck that you got this wonderful snow that makes everything so beautiful here. And it's wonderful to have you here to remember all the memories of Sam and to reinforce all our emotions on the subject. Thank you.
Without the snow when you're here seems to be a tradition.
And now, Jesus Gonzalez of Stuff is kindly going to tell us more about Sam's work and legacy.
Thank you very much. But let me begin by saying what a great honor it is for me to be in charge of reviewing the fine work of Sam. And thank you very much to the organizers for this great chance. So I have to confess that when I was really thrilled when I received this invitation for giving a talk in this conference celebrating Martin's birthday, happy birthday,
Thank you very much.
and in commemoration of our dear friend Sam. But I was really scared when the organizers told me that I should review Sam's work. The point here is that, well, through the quality of his contributions in mathematics, Sam is one of the towering leaders, figures in algebraic topology that helped through the beginning of the second half of the previous century, helped shape modern algebraic topology. So what I want to do now, it's quite difficult to do a full review of his contributions. There are many interests.
Is that a description of Sam up there? Fast, energy efficient,
I'm trying to get rid of it. Okay, so what I'm going to try to do is to just be choosing the most representative works that he has done through the history of his work, and try to give you an idea of what is behind all this mathematics and how it has impacted, affected the development of algebraic topology. Okay, so let me begin then by, here is a brief summary of the few topics that I will be discussing today. And any expert here in this room will, and I guess any expert will agree with me that the four topics in marketing in blue font describe the path that took the young Sam right after graduation to, in basically a little bit more than 10 years, to be one of the leaders in algebraic topology. This is just amazing for me. So let me just say also a comment that this path runs across what has been known as the golden age of immersion theory, starting with the work of Smale on the classification of immersions of Euclidean immersions of spheres, and going through the work of Gromov on the classification of solutions of partial differential relations. So this goes 60s, 70s, starting in the 50s. So the point here is that Sam's first summit moment, namely the definition and usage of this Brown-Gitter spectrum, which I will get to later in the talk, agrees with the summit moment in the golden area of immersion theory. But also, I would say that it sets, or at least it agrees with the golden era in algebraic topology, in homotopy theory, the 60s, 70s, and 80s. Okay, so let me begin by getting into business. So in those days, in the endings of the 50s, the immersion problem for manifold was very fashionable. So in general, you have an n-dimensional manifold and you wonder whether there is an immersion, or try to classify more generally the immersions of a given manifold in Euclidean space. Now, well, if you take the differential of this, that essentially tells you that the tangent bundle of this is a subbundle of a trivial bundle over n. Well, and then you can define the normal bundle associated to this immersion. Let me call this F. So F is nothing but just the quotient. So a way to think of this is by thinking that what the normal bundle associated to the immersion is, locally at least, is just a tubular neighborhood of the manifold inside, locally, the Euclidean space. Now, it's locally, this gives you a trivial decomposition of this map. So, means that you have a Whitney-Sum decomposition of the trivial bundle. Now, what Hirsch had proved, when, maybe 40s, 50s, is that actually you can recover the isotopy class of the immersion out of the isomorphism class of the normal bundle. So there is a one-to-one correspondence. So, well, this was the basic setting, and Sam started working on this. And the only thing, of course, that is missing is just the homotopy language. Namely, this began with work of Serre, Wu, and Hurewicz, describing in homotopical ways these kind of geometric arguments. But all the theory really was settled in a very systematic and clean and nice way by Stinroth, by the way, the PhD advisor of Sam here at Princeton. And of course, Sam learned this whole theory from the best. So, and it showed. So what you have then is the normal bundle. So I'm going to stabilize it. One consequence of this classification of Hirsch is that the normal bundle does not depend on the given immersion if you have enough room where you immerse the manifold. So that defines for you a stable normal bundle, and in the homotopical terms that corresponds just to a homotopy class of maps from M into VO. And then, well, just as in Alex's talk, so recall this is of dimension M, so you have the canonical classical maps, think of them as inclusion if you want, into the classifying space for vector bundles of this dimension maps naturally by stabilization into VO. And so the Hirsch result says that there is an immersion like that, there exists such an F, if and only if you have a lifting up to homotopy. In other words, the stable normal bundle has a realization as a vector bundle of that dimension. Okay, so that's pretty much the beginning of the situation. Now, what's the main idea? Well, it was classical that characteristic classes, let me call it omega, namely an element in cohomology on VO, which is non-trivial as a normal class for the manifold, give obstructions for finding immersions of manifolds. Namely, if this guy is mapping to 0 here, then this lifting, this immersion cannot exist because this would contradict this. This is kind of a classical obstruction. So what it was the starting point for Sam's work. Now, one thing to notice here is that in some cases, these obstructions are the only obstructions that you can really find to produce immersions. For instance, there is this general result by Whitney that says that any manifold actually immerses in R2n minus 1. And if the manifold is a product of projective spaces, say like that, where all the EIs are different from each other, then actually a witness immersion result is optimal. in the sense that this manifold will not admit an immersion in one lower dimension. And you can prove that just following that scheme. That's very simple. Just let me call them primary characteristic classes. Good. So, however, there are examples where you find that all the relevant characteristic classes, these obstructions, vanish, and yet you don't have the corresponding immersion. So the way to interpret this, at least Sam's vision of this problem in joint work with Jose Adam at the beginning of his career in the 60s, was to say, okay, there must be another layer of obstructions, some kind of higher obstructions for the desired immersion. And that's what they did. So essentially, one has to notice that the Stephen-Whitney classes of any bundle, here you take any vector bundle over a space, can be recovered in terms of the Thom isomorphism from the action of the Steenrod squares on the Thom class. So Thom isomorphism connects the cohomology groups of the base with the cohomology groups of the Thom space. And, well, then the wonderfully simple idea was, okay, why not to use higher operations instead of primary operations to produce higher characteristic classes, which could be used as obstructions in that scheme. So, well, the idea was not that revolutionary after all at that precise moment, because higher operations were already introduced by Frank Adams in his very much celebrated solution of the problem of finding maps with Hoffenberg 1. So, anyway, that's a good idea. So suppose phi, psi, or whatever phi is cohomology higher operation. Then, for your given bundle, you can construct, just by following the same formula, a characteristic class, higher characteristic class associated to this higher operation, just following the same formula. So you look at what happens here, look at the action of this higher operation on the Thom class. All right, there is a little bit of technicality here that I want to avoid. Namely, higher operations are not always defined, and when they are, they take values modulo some indeterminacies. But I'm going to skip those details. Those really is important. Well, it's important, but not for the purposes of this topic. So this way you produce higher characteristic classes. And, well, they wanted to use them in that context, and indeed, they amazingly produce in 2-3 years a lot of non-immersion results that many of them turn out to be optimal. In fact, this activity, this very intense activity, captured the attention of other researchers in the area, like Mahowald, Milgram, which quickly joined the group, and in very few years, a couple of years, they had developed the theory in a very nice state that would produce not only non-immersion results out of the existence of non-trivial obstructions, but also they were able to put the theory, just basically a modification of, well, a very primitive version of obstruction theory, to produce actual immersions from the knowledge that enough obstructions, higher obstructions, were vanishing. So, before I run ahead of myself, let me, pause here and make a summary what it meant to have these results, those results at that time. So the point is that those higher operations had a lot of information, a lot of common top information built in their definition. However, they were actually highly computable. I could give you an example perhaps later. The thing is that they use this information and produce non-immersion results, and then later on immersion results. And before all this work happened, before the 60s, there was basically one infinite family of optimal immersions for real projective spaces. Let me focus on real projective spaces. Namely, the one coming from here's the witness immersion, general immersion, which, as I just said, is optimal by primary considerations, namely just regular characteristic classes. But after that work, the situation did not change much relatively because the problem is still widely open. But now there are 7 families, or infinite families, of optimal immersion for real projective spaces. Now, a couple of interesting things is that 5 of those were already known at the end of the 60s because of this flurry of activities. And 2 of them were, of course, proven by Sam and his co-workers. And besides, the 2 recent families are also the positive side of the immersions are proven with those results. So my point here is that, well, 60s was a highly active decade of work in homotopy theory applied to this particular problem, and most likely Sam being the head of this activity. But, well, you will say, what's about the real projective spaces? Well, nothing really, but it's kind of a landmark. It tells you, or it gives you the opportunity to develop new methods that will really become very important. It's like Steve Wilson said, you can go at that time, Sam went to this not old problem, but fashionable problem, and obtained these results, and said, impressed the old guys at that moment, and said, okay, here are the results, very good, but wait, I have a very strong tool, which with the time became one of the central tools in homotopy theory, as I will try to make my point through the talk. So this essentially shaped the development of homotopy theory through the following 20, 25 years coming. All right, so I'm not saying this, neither that. So, well, can I use that one? Doesn't matter. Now, I already said that Sam's vision at that moment was to think of these higher characteristic classes as obstructions for the existence of immersions of manifolds. The idea, again, was not such that revolutionary. Namely, it had to be motivated by the previous work of Posnikov and Moore, as refined later by John Moore, that essentially says, well, if you want to understand, like in that map, no? you want to understand liftings up to homotopy. Well, you want to, in general, suppose you have any map, from E down into B, and suppose it is a vibration that you really don't need to, and if you don't want to, but that's just any map from topological spaces. And I want to understand the difference, the homotopy difference between the 2 spaces. Well, one way of doing that is by looking at the homotopy groups of the homotopy fiber. So, okay, so what these Moore-Posnikov methods are is that you can decompose that information into a tower of maps I prepared my talk. You can decompose this sequence of the original map as the composition of an infinite tower of maps. And in such a way that any 2 consecutive things, together with the map that join them, map from one to the other, are encoded, the homotopy information in that portion of the tower is encoded by one single homotopy group of the fiber. So suppose F is the fiber of that. Homotopy fiber. And of course you want that the sequence I0, I1, and so on is strictly increases. It swaps all the dimensions where the fiber has homotopy information, and even more, you want that E is recovered as the homotopy limit of these guys. So that's basically what is about this tool. Now, a less fancy way of saying this, so I guess I want to
So
put...
the other side, the other side, right in, right in. There.
Right.
Oh, what are you looking for? Sorry, what do you want?
I want to lift it.
Oh, you want to lift it? I see. Sorry, I did, I misunderstood. And you want the thing has to go off, so you're finished with this.
No, I
Like, projector's going to stay on unless we turn it.
well, I can use these two and then go back to this one. I don't want to rewrite this.
Do you want the projector left on?
I don't mind. Do you want the light on? Do you mind by leaving the light on?
Keep it. As I said,
So, as a technical way, or perhaps a non-technical way of saying that these homotopy groups encode the information on this portion of the tower is by saying that, okay, if you have here this portion of the tower, if you have any map from any space into En, then I would like to understand whether or not I'm able to lift it through this portion of the tower. And everything is encoded by a single element, namely the nth Cosmical invariant, which is some element in the cohomology of the base, with coefficients in that homotopy group of the fiber. So, technical reasons, there is this element, so that you have that it lives through here if and only if it maps trivially under G equals 0. So that sets a whole family and a complete family of obstructions for lifting a map G from here into there. Namely, you have to start trying to lift it little by little, understanding these obstructions. There's again indeterminacy, just as in the case of higher operations, just coming from the fact that this is not necessarily unique, nor even up to homotopy. But anyway, it gives you a way of trying to decide whether a map or not, whether a map lifts or not through this part of the cosmic tower. However, this method is not well suited for concrete computations. And the reason is that it really depends on very difficult to compute information. Homotopy groups of spaces in general are very difficult to compute, and so, well, you need to compute the cohomology of that with these coefficients, and even then identify explicitly the invariant. So that's not of good use. Well, it has many uses, but for the kind of result that they were looking for, it was not good. So the idea is that, okay, then in the mid-60s, together with Mahowald, still in the 60s, they modified this procedure. What did they do? What did they do? Essentially, okay, the problem is computing this part in the method. Now, at that time, Frank Adams had introduced this spectral sequence that we have been hearing about, the Adams spectral sequence that compute homotopy groups of space, at least at that moment in a certain range, but then we know that Martin was involved in putting all the complete range. So, well, let me go back a little bit to what that meant. So, Adams proved that the homotopy groups of any space, like the one that I have over there, can be approximated, or there is a spectral sequence converging to at least the completed part of. I don't want to be very technical. There is an object here, there is a machinery that approaches these groups and can be obtained, can be algorithmically computed, at least initial approximation, from the cohomological properties of the Stingler algebra. Namely, you have to take the cohomology of F, think of this as a module over the Stingler algebra, over the algebra of all operations, and resolve it. If you do this in a very efficient way, what you would get is, at each stage, you would have a basis. 0, 1, and so on. And those elements would be precisely the beginning of things that will detect homotopy groups. Eventually, some of them will die in the way, and some of them will stay approaching the homotopy groups of F. Now, the usual chart that we have also been hearing about is that, well, you have 2 degrees. You have the filtration degree, the Adams filtration degree, which is nothing but the homological filtration in this resolution. And it is written in this axis. And then you have a total degree, namely the fact that this is a graded object. Everything is graded, so you have a total degree. And you use it here by subtracting the Adams filtration, just because when you compute the derived functors of the homomorphic functor, namely this object is an x, st has 2 degrees on the cohomology on the cohomology of F, sigma 2. I hope I got it right. What you would get is that these groups having t minus s a fixed value will be piled up here, given the first approximation of the homotopy groups of the fiber. Now, what's the point with all this? The point is that, well, this is a algorithmically computable thing to do. It's very hard, but you can actually have a computer to do it for you. But this is only the first approximation. And the fact is that if you want to understand what is beta S, you really have to understand what the first guys are, at least in the relevant total degrees. So that means that these guys are elements lying in the first line. Well, sorry, these guys lie in the base where S is 0, and then you have these guys, and then you have these guys, and so on. So if you want to reconstruct this homotopy group, it's hard if you want to put it into the Postnikov method all at once and forget about it. It's more natural to put all these elements in the several, in a given filtration, all at once, and wait until you finish up one of the every single homotopy group. So this is what they did. They incorporated this method using homological algebra into the Postnikov, Moore-Postnikov method, and the result was a machinery, nothing new, but very efficient and highly computable. Highly computable. So, good. So the way was paid for the next steps, and it was Sam himself that gave the critical step. I have to use that. Okay. Oh, yeah. So what was the idea? I have said that they liked higher characteristic classes as obstructions for immersions. So in a very ambitious project, together with Ed Brown, actually Sam met Ed Brown right after finishing grad school in the 60s. He had a position, a postdoctoral position visiting Brandeis, and he met Brown there. But it was only until 1972, in the summer, where Brown was visiting Mexico, that they started this very, very ambitious project. And what is it about? Well, so let me go back. Yes, I erased it. To this thing. Okay, now suppose, I know that characteristic classes that go trivial into here are useless. They will not give me obstructions. I want something that goes non-trivial here to begin with. So their idea was, again, very simple, but very important. Namely, let's just get rid of all those all those Stephen-Witten classes that vanish universally on all the manifolds. That was understood at that moment. It's not difficult to describe it. So that gives you a bunch of guys of this so that the normal moment of n is 0. I don't want those guys. So essentially, I'm killing those with an I greater than m minus alpha of n, so that here alpha of n is the number of ones appearing in the binary expansion of n. Number of ones in all right. So how do I get rid of those? Well, I can think of those as being the first Postnikov invariants that I want to get rid of, namely these guys. These guys, these guys. Each one of these elements was an element in the homotopy groups of the spheres in some given centration, and then you want to reconstruct the whole thing. Well, you can kill those elements and think of those as being here. Let's define them to be K0. It's a bunch of them. And then take a fire. Or take the Moore-Postnikov process for building a Postnikov decomposition of something. The problem here is that that something was not known. So this goes the other way to what I described, just described. Namely, if you had a space, or you have a map from E to B, and you know the difference, namely the homotopy groups, then you can start decomposing it in terms of the cohomology classes that have all the homotopy information. But here you're doing it the other way around. You have nothing, and you would like to describe some space out of something that you believe that it would have certain nice properties. So this really requires a lot of knowing, a lot of geometrical intuition, knowing what you really want to do, and at the end, they completed the work and produced this very nice topology paper in '73. Now, what was the motivation? The motivation is they were very successful in saying, okay, if I have a primary obstruction, which is trivial, then by relations among the operations, I can have a secondary obstruction. And those are sometimes non-zero. So they said, let's do this in the more systematic, organized way. The idea has some madness ingredient. Namely, how in the world can you get information, non-trivial information, out of trivial information, even if it is higher? Well, sometimes miracles occur, and you can get brilliant results from these situations. Unfortunately, this was not the situation in in Sam and Brown's case. But not yet, not immediately. At the end, they constructed the inverse limit, well, the homotopy limit, and defined these very nice spaces called spectra that were called the Brown-Gitler spectra. Now, it's gonna be a little bit, So I have to turn this. Will this turn it on?
It'll take a little bit, but
You want it back on? We need the screen.
So I have to tell you what
Do you want the screen?
yes. I want to tell you what a Brown-Gitler spectrum is. However, that is very technical and is not suitable for the purposes of this talk. So what I'm going to do is apologize for the following words. So here it is. What is a Brown-Gitler spectra is that. Thank you. So let me still be a bit more. However, what I can do for this talk is say a few words about how important these objects were for the development of homotopy theory through the following years. So, well, there are several nice applications. Like I have like 20 minutes left.
yeah.
So, I'm going to mention 4 applications which lie in the heart of homotopy theory, right in the core of homotopy theory. There are a lot of applications that I'm not going to be mentioning, but those are, I guess, some of the most representative ones. So, to begin with, of course, although it's more or less the same time when all the first 3 were, all of them, I guess, starting to pop up. But the first one is, for obvious reason, the immersion conjecture. So what is the immersion conjecture say? Well, there is a result of Massey maybe in the 50s, I'm not sure, that says that, well, for any n-dimensional manifold, all the normal characteristic classes vanish if I is greater than m times alpha of n. That magical number. Now this sort of result has a possible explanation, which is, well, this is implied if I knew that this manifold, and remember this is any manifold, were to immerse in dimension 2m minus alpha of m, because then the normal bundle associated to that will have dimension n minus alpha of m, and then the high characteristic classes will vanish. So this became known as the immersion conjecture. This much. Namely, the following statement, that for every manifold of a given dimension m, that manifold would admit an immersion in dimension 2m minus alpha of m. And of course, this result would take to the limit, to the best possible situation, witness a general immersion of manifolds of dimension n into dimension 2m minus 1. All right. So what is next? Oh yeah. Now there is by the end of the 70s, I guess. So now how does this work? It's going to work. By the end of the 70s, Brown and Peterson have developed a method to prove that conjecture. And it had basically the following form. Problem. Namely, they constructed a space, not a spectrum, not a technicality. They constructed a space space, let me call it Pn minus n. And a map, and that Gn minus n. so that cohomologically it had the same, it looked the same as the one on the right. Namely, this is a surjective map killing those classes detected by mass. Well, they want with an index greater than that number. But more importantly, they show that the normal bundle of any n-dimensional manifold will always admit a lifting into this space. That's what they did. And they were hoping to show that they could produce a map from there to there, so that filling the optic homotopy is that commutative diagram. And then you will get the general immersion for the value, the right value for associated to the immersion conjecture. Namely, I'm having everything screw up, n minus m. This is m, trying to immerse in R2m minus alpha of n, so that n is m minus alpha of m. Unfortunately, they didn't succeed in producing this map. But in '84, Ralph Cohen gave the complete argument proving how this map could be constructed. And essentially, the idea is, again, very technical, but it depends on the following observation, that the Thom space of this map, this is a stable map, this is a stable vector bundle, so it has a Thom spec, actually, associated. This spectrum decomposes as a wedge sum of some things, some of which, or maybe all of them, I'm not sure, are Brown-Gitter spectra. And there should be all of them Brown-Gitter spectra, because they use this decomposition to construct, actually, a map into here. Namely, what Brown and Peter did know was that this diagram could be completed after Thomifying. So you have here two stable vector bundles, and if you Thomify it, then you have the corresponding map. And the hope was to de-Thomify it and produce the map on the nose. And that was done using these were Brown-Gitter spectrum. So this was one very nice appearance of these objects. Then there is the Siegel conjecture and another related conjecture by Sullivan that says it deals with the possibility how to map out of the classifying space of a finite group. So suppose G is a finite group. Then you can consider the Burnside ring associated to G. Namely, this is a kind of a Grothendieck construction. You take finite sets which admit an action of this finite group, and then take formal differences of those guys. This is a ring where the sum comes, where addition comes by disjoint union and multiplication comes from Cartesian product. And now the cardinality function gives you a morphism from here into the integers. So that, and you can take this lepimorphism, it's called the augmentation morphism, and you can take the kernel, the augmentation ideal. And what Siegel's conjecture claimed is that this picture, not really topological, nothing, it's just sets, groups acting on sets. This group, the completion of that thing is related to homotopy theory, because there is an isomorphism from this ring into the stable cohomotopy groups of BG. That is to say, maps from BG into the sphere, stable maps into this sphere spectrum. Now this was motivated, this is Siegel's conjecture. It was proved by Heinz Miller in, no, it was proved by Gunnar Carlson first in 84, roughly in 84. And it was motivated by previous work by Atiyah, which said, okay, there is a similar thing going on for representations of the group, and you can also take a completion of it. And Atiyah showed that there is an isomorphism with the KU cohomology in degree 0 of BG. So this is some sort of a general, well, it's related, it's similar. Now, the proof of this, given by Carlson, was basically algebraic, I believe. He used essentially the cohomology of the Brown-Gitler spectra. He built on those and produced such an isomorphism. So let me just say that much. Then, later, comes the Sullivan conjecture, that asserts, where am I? I'm lost. I'm completely lost. That asserts well, it has a similar flavor. Namely, it has to do with maps out of the classified space of any finite group. But there are two main differences. Namely, you don't have to stabilize the map. You just look at the maps. And the other big difference is that you don't have to map into sphere. You can use any finite CW complex. So the conjecture is that if you look at the function space, just the space of functions, from the G into X, these are free maps. This has the weak homotopy type of X itself. Now, Miller proved this result again by the same time, 84, essentially by noticing that this is equivalent to saying that, well, if I want to fix base points and then I want to look at these things, then the homotopy groups of this space, this is for the base space. Let me just use a 0. So this function space of base maps out of a classified space of a finite group into a finite complex has to have trivial homotopy groups. And the way to prove this, again, was using the Allen spectral sequence. And I believe he used the Brown-Gitler spectra, to produce to approximate this guy out of auxiliary spectral sequence, as we just saw in his talk. He likes to do that approach. And one of those initial spectral sequences collapsed, and for that, the use of Brown-Gitler spectra was fundamental. Am I right? Sure. Okay, so that was the third application. By the way, this Sullivan conjecture implies a very famous also conjecture by Serre, that what Serre did was to study the homotopy groups of spheres, just plain homotopy groups, not stabilization. And he showed that the homotopy groups of spheres have lots of torsion, right? For any prime P, you have that pi k of S I of S k, say, tensor with z mod P for any prime is now 0, as long as k is, of course, greater than 1, for infinitely many i's. And then Serre conjectured that the same thing holds if you replace the sphere by any finite complex, as long as it is possible. Namely, it has to be simply connected, and it has to have homology, at least some homology in a finite number of dimensions with p torsion. If that's the case, then the same conclusion applies. And that's a consequence of the Sullivan conjecture. But in the roots, you have the Brown interspectra. And finally, the other application is the doomsday conjecture, namely that I already talked about the atom spectral sequence and how you build it, the usual chart by layers. And now this conjecture claimed that in every filtration, in any atoms filtration, you would only find a finite number of classes which actually detect homotopy groups, elements in the homotopy groups of the sphere spectrum. And by that time, there was plenty of evidence. Let me tell you. For instance, Adams's work just said that in filtration 1, indeed, you have only 4 elements having detecting homotopy groups, and all of them were accounted for the Hoff-invariant 1 elements. And if it were not for this work of this was by Mahowald using the Brown interspectra, if it were not by that, maybe we still would have more evidence, namely Hill, Hopkins, and Ravenel's recent result on the Kerberian-invariant 1 problem would also shed light on this possible conjecture, namely there are only at most 6 elements in the line 2, in the filtration line 2, which detect frame manifolds with Kerberian-invariant 1. But there might be another type of element. And that's what actually Mahowald did, dooming the doomsday conjecture. Namely, he used the Brown interspectra. He showed that certain spaces, for instance, this one, 9, stably decomposed in terms of some of the factors, some of the summands, stable summands, are Brown interspectra, and that easily, well, unquote, led him to produce infinite families of homotopy elements in the spheres. All right. So I have another topic. So the conclusion here is that the Brown interspectra, I think, is one of the main contributions of Sam. It put him right in the eyes of the world, and it was these Brown interspectra were popping up all over the place in that time. In fact, there was a symposium that was organized by the AMS at that moment in '85, just to understand the topology of this subject. But now I want to switch gears and try to steal a couple of minutes more from you. There are 2 more topics that I want to say about the work, more recent work of Sam. One of them is historic topology. I apologize for that. I am not prepared for doing that. Anyway, we had Santiago's talk and many talks on toric topology, and it's all clear what's going on there. So let me just now focus on some work that he did. This is a fine piece of work that should also be mentioned. And besides, this is a very, very convenient. It comes to this. It's a great topic to discuss in this talk, because that was joint work with Martin, our birthday man, and I believe this is a very, very fine work. So what's ongoing on? We've all heard about configuration spaces. I'm going to skip that part. There's not much to say about the definition. But Sam was interested in the cohomology properties of those spaces. So as far as I know, there is no method to compute the cohomology of these spaces with any coefficients. Although there are 2 spectral sequences that work best when M is a manifold, this can be defined for any topological space, there is the right spectral sequence associated to the inclusion of these into the a Cartesian product of M. And there is this spectral sequence that Martin and Sam introduced. Now, I want to compare. I want to say one point about this work. In the 70s, Fred Cohen had studied with Larry Taylor, had studied in quite detail this spectral sequence. And in particular, he understood the initial term of that was known, and the second differential of that. The first non-trivial differential, depends on where you want to start grading the differential. But he understood the first non-trivial differential. So you had a nice approximation to the cohomology. This was multiplicative spectral sequence, so you have a nice approximation to the cohomology of these objects. Now, on the other hand, these guys used simplicial methods to do the same thing. They actually constructed a bi-cochain complex, and it comes equipped with two filtrations. One of them they used for the spectral sequence, so they identified the first differential and identified what was left. I guess, yeah, that's the E2 term, which agrees with that one. So they identified the thing, and they both agreed. The E2 term was known, so you put it like that, and they agreed. Should be, now did you identify the E1 term, the first differential, and then what was left?
Pretty much what happened, yes.
It's the same situation like this. So you have the same beginning. I just screw up things, but the two spectral sequences have at some stage the same, look the same. Maybe you have to use rational coefficients, look the same. And then they, of course, converge to the same object. And now, back to this one, now this paper appeared in 91. In 96, say 5 years after this Martin and Sam's work, there was a paper by Totaro and another by Igor Chris that showed that this spectral sequence, after this nice term was identified, this spectral sequence collapsed if the manifold was a complex projective variety. Right? That was very nice, but Totaro himself asked about, well, do you really need that this is a projective, a complete variety for the collapsing, or he was asking for another maybe orientable manifolds in which you have this convergence, this collapsing phenomenon. And well, actually this stood as unresolved until 2013, I guess, from what I found in the AMS. However, the answer was already in this paper. And the point is that, well, these guys actually proved that these collapses for rationally formal spaces, right? So that implies Totaro's result, because they have the same starting, the same ending. One of the collapses is a rational coefficient, so you cannot have any further differentials on the other. So that implies half of the result in Totaro's 96 paper. It does. I don't know if you care about the multiplicative structure, but let me not touch that for the moment. The thing is that you did actually more. Here again, very nice intuition, and they said, okay, and we conjecture that higher differentials in this spectral sequence, in the case of non-formal space, has to do with the existence of higher massive products. And you did not give further indications more than the methods that you were already using. Maybe for an expert would be clear. And well, in that year, Felix and Thomas proved it. Well, at least constructed a family of manifolds having non-formal, rational formal manifolds having strange higher mass products, which gave rise to differentials in I don't know even, maybe in this one, but it's equivalent in all of them. So indeed, that conjecture was nicely done, and I think this is a very, very neat piece of work that they did. So let me just finish by saying that Sam had a great vision to create leading working groups. As while he was the chairman in Rochester, Doug Ravenel and Fred Cohen joined the department, and this just reinforced an already very strong department, creating one of the leader groups in the world for homotopy theory. And of course, in a much lower scale, I have to say, 20 years before he had founded the Mexican topological school of algebraic topology. So these are, I guess, very, very comparable to what I've said here, achievements. And also, what was the other thing? Okay, well, let me just finishing that, saying that behind these incredible mathematical abilities and behind this charismatic leadership, there was a very charming man, a caring person, that anyone approaching him would find immediately that he would do his best to give for students, for friends, and for family. So for all those reasons, I think that Sam will always live in our minds and in our hearts. Thank you.
Does anyone have any brief thoughts or anything they'd like to share about Sam or his work? Does anyone have any questions for Jesus? Would they like him to prove a favorite theorem of theirs?
You also mentioned that he brought John Moore to Rochester.
Yes, sorry. Forgot that. Yeah. Good point.
No, I was there before.
Well, it sounds like everyone's anxious then to get to dinner, where I'm sure much more colorful stories about Sam can be shared. Thank you.